not particularly relevant topology. All right, I'll begin with a word of prayer finally. Heavenly Father, we thank you for this day. Thank you for these students. Just ask you to bless our class today, Lord. In your name I pray. Amen. All right, so let's see here. So I wanted to go back to section 12 one more time and just write down some of the high points because they're contrasted in section 13. All right, so here's the big idea. Product topology. So what was the definition of the product topology? Let's see here. Come on. So let X be the product alpha in some index set A of X alpha, right? He says, has base. What's the base for the product topology? Sets of the form X and X such that X of alpha j are in U alpha j for 1 less than or equal to j less than or equal to m, where alpha 1, alpha 2 to alpha m is a finite subset of the index set A. He says, in other words, the set U, he says the set, he starts talking about this set U, but I don't think he's wrote, the set U is defined by restricting a finite number m of its components to lie in open subsets of corresponding blah, 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 other components non-restricted, but he never said what U was in this. It's kind of funny, unless I'm missing it. But I'm pretty sure the U he refers to is this guy. This is U. So I drew a picture on the board when we were in the lab room to illustrate this. It's like you're restricted to be in an open set in like one of the factors, but then the other directions are unimpeded. And then if that's the base, that means unions of those things, right, form the open sets in the so-called product topology. In contrast, right, so I mean, just for an example, I think the example where I can just kind of, I'll draw it somewhat, schematically, if you will. If this is like, this is the x2 and this is x1 in some sense, right? Then a basic open set here in the product topology is like a strip, right? So it's something like if this is U1 open in X, then this is something like that, right? This would be something like what? X comma Y such that what? X is in U1, Y free. So that's something in the basis, right? But you got to imagine here the product could be infinite, right? So it's just saying that there's a finite number of them that are stuck in the open sets for, a finite subcollection of the index set. In contrast, there's the box topology. Box topology on the same set. So still talking about the infinite possibly infinite Cartesian product. All right? Has basic open set of just the product of U alpha, alpha and A. So let's say U equals that, where U alpha is in the topology for X alpha. So this is, I mean, what's that? It has many more open sets, right? So it has many, many more open sets than the product, right? Because you could take the case that U alpha is equal to X alpha for infinite. I mean, if you consider, if you just imagine take U alpha equal to just X alpha for all but finitely many of them, then you're back to the sort of thing that we were talking about for the product topology. Does that make sense? So like, if you just set U alpha equal to X alpha for alpha not an element of alpha 1, alpha 2, alpha m, as we were talking about over here, then this U would be this U. Let me call this U tilde. So in other words, every open set in the product topology is also in the box topology. But there are many, many, in the infinite case, open sets in the box topology which are not present in the product. So that's a finer topology, right? Or I would say it's a finer topology. I think in the language of Gamelin, he would say it's a larger topology. Okay? For the same set, for the same Cartesian product. Okay, then I just wanted to spend a minute or two talking about that. These are an equivalent in the genuinely infinite case. All right, the main thing being that Tikhonov's theorem says that if you have all of these being compact, then the infinite product with respect to the product topology is compact. This is Tikhonov's theorem. And that's just not true for the box topology. And then Theorem 12.1, this sort of characterizes it. It says the product topology which we'll just omit the index set here for a second, pi x alpha, is the smallest topology for which each projection is continuous. Okay. So you know what it's easiest. So I mean, here's this is not terribly useful, but pi 1 of xy equal to x. But the notion of projection here is much more general than that, right? I mean, it's not just a list, it's a function, right? Like the projection is defined for something like this, right? Pi alpha of x is equal to the, I don't know. I mean, it doesn't seem like I'm saying anything there. He gives a careful definition in here anyway. Do you have some? Okay. All right, so again, the product topology is the smallest topology for each of the projection maps is continuous. And then theorem 12.2 says if you have a function from a topological space E, come on. Theorem 12.2, if you have a function going from, what's the domain? Sorry, keep losing my place here. From E, yeah, of course, duh, I should know that. From E to the product of x alpha like that, all right? Then this is continuous if and only if, you know, the product P alpha composed with F is continuous for all alpha in the index set A. In other words, the function into a product is continuous if and only if each of its component functions is continuous. The thing that kind of blows my mind here, relative to previous conversations in other courses, is there could be infinitely many components. So that alpha could be like a real index or something. It could be a complex index, whatever. It could be a p-adic index, I don't know. Don't ask me about that. All right. So that brings us to, oh man, whoa, the sun. I need to get some kind of like covering for that window, something. Maybe just like if I took a couple pieces of paper, taped them together, like rolled them up, just bring it with me to class just in case, you know. Some kind of, it's getting on my nerves. Anyway, all right, I digress. Quotient spaces. So we'll be on this topic for a few days, but I'm going to do my best to talk to you guys about what's said in Gamelin here, at least today, all right? And I think he's beautifully clear. I think it's so clear what he says in here. So I'm really looking forward to trying to explain it to you. The idea of a quotient space, right? So product space, he says, I mean, this is kind of a natural thing to talk about. We like thinking about taking the reals and constructing R2 or R3 by taking the product of the reals, right? So what's a quotient space? What's that idea? It's something like, you know, if I had oh, there, maybe that'll work. Oh man, I can't disconnect those. Phooey. Now maybe you could take a line segment, right? And if you could take these 2 points, right, and like somehow connect them, right? It seems like you could take this line segment and make it into a circle, right, by just attaching those 2 points. All right, that's roughly speaking an example of a quotient. Or you could think about taking this rectangle, right? Oh, hey. Fortunately, King couldn't staple his. Woohoo! So, what's that? Oh, that's scratch paper. Oh, I should. No, oh, yeah. Okay. Yes. All right. Respect. So, you know, we could take a rectangle, right? And if we could attach one end to the other, right? If we could identify the points at one side and another as being the same point, then this would be an example of a quotient. If in addition, you could also identify, I don't think the paper is going to survive this one. If you could also identify the other, and then if I could somehow blow that up, then we'd have a what? See if I could just, what's that? It's a very poorly crumpled torus, but yes. So how do you formalize these ideas, you know? And so basically the concept, let's just say we're identifying this side with that side, right? That would give us something like this, right? And then here's the place where we glued it, you know? So at the heart of all these constructions is this notion that some points are being left alone, right? And other points are being identified. That's the first kind of quotienting you could do. But you don't actually have to have the situation that there are points left alone. You may be collapsing, maybe every point somehow gets messed with, all right? But this one here, the equivalence relation that corresponds to that would be something like, if this is 0 to 1, right? We're saying something along the lines of x is equivalent to x only for, 0 less than x less than 1, and then also that 0 is equivalent to 1, right? I mean, you could say for x equal to 0 or 1. And that would define an equivalence relation on the closed interval from 0 to 1, right? Because it's reflexive. Well, what would it define an equivalence relation? Let's see here. What's that? Include 1. Oh, okay. Yeah, sure. I got you. Okay, so then you're like, I've defined reflexivity for the, okay.
0 is not.
And then how about symmetry? If x is related to y, then what's the deal? Either what? If x is not equal to 0, then what? That means that y is equal to x. So then that implies that y is related to x just the same, right? I don't know. I'm sorry. I'm somehow making this confusing. It is not confusing. There is an equivalence relation, which, yeah. Yeah, the equivalence relation to do this gluing would be any point in the open interior of the rectangle, right, except for these edges, right? I don't know if those are I don't know if those are dotted or not, whatever. That's not the point here. So like this point and that point are identified, right? So if this is P and this is Q, then P is equivalent to Q, but otherwise, we just take each point in here and just say x is equivalent to x, but it's not equivalent to anything except its own, they're just equivalent to themselves. All right. So he points out that, he says, spaces obtained from a given space by welding or gluing subsets together are called quotients of the given space. And he points out, like, a torus is the quotient space of a rectangle, obtained by identifying both the length and the width edges together in the appropriate way. But he also says we should apologize because, in some sense, this quotient is not an inverse operation to the product, as you might be tempted to think. I mean, so often we take a product, we take a factor, and there's some sort of like inverse relationship or something. That's not the case here. It's not like quotients are inverses of products in this sort of stupid sense. But okay, so definition then. Here we go. Let X be a set. All right, and an equivalence relation on X on big X. And here I'll throw in some notation. So like the equivalence class of X would be Y in big X such that what? Right. So what can you say about the equivalence classes? Equivalence classes up till the partition X, right? Into pairwise disjoint subsets. Whose union is X. All right. And so the set of equivalence classes is as follows. So we use X mod squiggle. That's going to be the set of equivalence classes, all right? This is the quotient set of X modulo the equivalence relation, all right? The quotient set of X mod the equivalence relation. And we define pi. Pi of X is equal to what? Right, so X, the element X maps to the equivalence class generated by X. So the natural map. In the case that the equivalent, I mean, here's a specific example of this. X could be a group, right? Like an abstract group. H could be a subgroup of X. Then we could use the coset equivalence, right? 2 points in the group are equivalent if they are in the same, say, left coset of the subgroup. All right, so like this could, in that context, this would become the usual coset map. Like pi of X would be X times H or X plus H if we're in an additive context. So this maps previous usage of pi, if you remember from group theory, you know. But anyway, it doesn't have to be that. This could be whatever kind of crazy equivalence class. I mean, there's no group structure necessarily associated with the equivalence class, right? I mean, it could be abstract and geometric like we started with. Okay? So then that's a set, right? And we're in topology, so what are we going to describe on the quotient set? The quotient topology, right? So what's the topology given to the quotient? He says where U, a subset of X mod tilde, is open, if the inverse image under the natural map pi view is open in X. So now I've added some more, right? So I started out by just talking about a set and equivalence classes, right? At this point, I've assumed something else about X, right? X is a topological space, which means we have a notion of what's open. So this is the definition. In the quotient space, the open sets are those whose inverse image are open in the space that you're folding. So what does this mean? I mean, he says that this definition is the minimum requirement that the projection be continuous. All right? And he points out that the useless topology will also work, but we don't want that. We want this to define the topology on the quotient space, the so-called quotient topology, all right? And he says, okay, so since the inverse image of a function does what? Preserves unions, and what else? And intersections, he says the quotient topology is indeed a topology. All right. So by the properties of functions and inverse functions I wrote on the board the other day, apply those to pi. Pi is a function, all right? So its inverse image satisfies, it preserves unions and intersections, right? And then he says that brings us to an analog. He says Theorem 13.1 is the analog of Theorem 12.1. And so here's Theorem 13.1. And you guys decide whether or not we've proved this already. I don't know. He says, let X be a topological space with equivalence relation squiggle. Then the quotient topology for the set of equivalence classes is the largest topology for which the projection is continuous. Does that make sense? When we say largest, we could also say what? I was saying this earlier. A lot of books would say, yeah, the finest. So let's see here. I guess is the projection map continuous with respect to the definition which we've written? Is the inverse image of open sets open? By definition, yes. So essentially we have forced the continuity of the projection map by our definition of the quotient topology. So to prove Theorem 13.1, I feel like there's only kind of one thing missing, which is what? Like, imagine, take a smaller, try to take a smaller topology. What would that mean? Yeah, if we had somehow a smaller topology, let's say t tilde prime, so that would be missing let's say V, which is an element of the topology in the usual, I'm using tau sub tilde for the usual quotient topology, right? And yet V is still, V is still, pi inverse of V. Well, that's an open set by assumption. But it's not, but V is not open. This is not quite the right logic here. I'm sorry. I don't know. What's wrong with me? I can't. Can you guys think of how to say this? Let you say, okay, so let tau be a topology on x quotient tilde, such that what? Then prove that tau is a you say a subset? Is a what?
Like that T is coarser than the quotient topology. So it's a subset. T is a subset of the quotient topology.
Which I'm using tilde for at the moment. So here I'm saying U is an element. This defines U as an element of the quotient topology here. Okay. Mm-hmm. Open in X, right? Oh yeah, therefore. Thus. U is an element of this, right? Yeah. Okay. All right. I'm going to move on. I don't feel like we're going anywhere. I feel like we're kind of, I don't want to say we're treading in water. I feel more like we're just standing in a baby pool. I don't know. Anyway, it's not good. Let's go on. Let us move along here. I have something more to say. So that's the analog of theorem 12.1, right? So the product topology is the smallest topology for which the projection is continuous. And theorem 13.2 is analogous to theorem 12.2, and it says, come on. What does it say? With all the usual bells and whistles here, let pi from x to the quotient set of x by tilde be the projection map a function f from x mod tilde to a topological space Y is continuous if and only if f composed with pi is continuous. Now I think we actually have something to prove, all right? So let's try to prove this. How would we prove this? I guess we'll go this direction, right? So suppose f from x mod tilde to y is continuous, right? Then f composed with pi, right, is the composite of continuous functions and is thus continuous, right? Because we proved that, well, first of all, we know by construction pi is a continuous map, right? Essentially by the definition of the quotient topology, this is forced upon us. And we're composing two continuous maps, which again is continuous, right? We proved that carefully the other day. So then how about the other direction here? So suppose f composed with pi is continuous. I guess we should do what? Pick an open set, right? Now, f composed with pi, excuse me, let V be open in Y, right? I'm trying to prove that f is, what was it? Oh, okay. I'm trying to prove that f is continuous, right? Why is f inverse of V? How can I use pi on that?
Use the whole function.
So forget about this for a second and look at what? And should I look at the inverse image of what of that? Of V? Can I do that? Oh, yeah, of course. Duh. Then what do we know about inverse images of composites? They sock shoes? So this is pi inverse of f inverse of V. Right, which exactly that implies that F inverse of, now why does F inverse of V have to be open? Because we are assuming continuity of F composed of pi says that the inverse image of an open set is open, right? So this is open in X mod tilde, right? Did I do it wrong? Oh, it's open in X, excuse me. Yeah, thank you. Yes, open in X. But that being open in X means what? Means that the only way this can be open in X is if this was open in where? In X in the quotient set. And if that's open, of course, that being open is what we're after, right? Because we want to show that the inverse image under F of an arbitrary open set in Y is open. But that says that F is continuous. It takes a little while to become accustomed to the definition of quotient set. I mean, it's somewhat unsettling at first, experience, at least my opinion. Okay. Now, next up, so I thought it'd be fun to put both of the section 12 theorems up on the board and the section 13 theorem, so we could actually see the parallel directly, Yeah, from smallest to largest, yes. Okay, so theorem 13.3. Come on here. Says if we have F a continuous function from a topological space X to a topological space Y, all right? And let tilde be the he says be the equivalence relation on X such that F is constant on each equivalence class. What is that? Let's write that out. So that is this equivalence class, right? Equals what? Let me call it X naught. So that equals X and X such that what? F of X naught equals to? I'm trying to write down as a set what he's said in a sentence. He said the equivalence relation on X such that F is constant on each equivalence class, right? So like for X to be another point in the equivalence class of X naught, what's that mean? It means F of X naught has to be equal to F of what? F of X, right? So what are these? I give this another name, if I call this thing y naught, maybe you'd not be surprised when I write that this is the inverse image under f of y naught. Or if you wanted me to write it in a kind of more, less, I mean, if you say y naught, then you could also write this. In other words, this is what? What's this equivalence class? We had another name for it. We talked about this the other day. Kernel? Kernel is an example of this, yeah. But this is it's a fiber, right? This is the fiber equivalence. So we've gone from a kind of abstract equivalence relation, right? Now we're talking about the equivalence relation which is induced from a given function from one topological space to another, right? This is the context. He said, then here's the punchline, then there exists a continuous function, G, continuous from x, from the quotient set of x by tilde to y, such that what? F equals to what? Yes, G composed with pi. So here's a picture basically of the proof. We take x, right? Map over here under f to y, right? And so I guess down here we could write x mod tilde like so, right? This would be the what? Start with x naught, right? Maps down to what? The equivalence class of x naught, whatever that is. This is the pi map. So this function, this theorem is claiming that there exists a continuous not just that the map exists, but it's a continuous map from where? From here to there. And G is equal to what? Oh, we don't know what G is equal to, but the claim is that F is equal to pi composed with G. So how do you think we should construct G? Let G of the equivalence class of x naught equal to what? Do you guys agree with Kang? What do you think? F of x naught? That makes sense. I think that makes sense. But that begs a question, right? Because x naught equals to x1 does not imply that x naught equals to x1, right? So when I make that definition, it begs a question, is G single valued if I so define it, right? If x0 equal to x1, then what is it? F of x0 equal to f of x1, right? Thus, G is well defined because it is independent of my choice of representative for the coset. Well, excuse me, for the equivalence class in this case. Coset is too specialized a term here. Does that make sense? Now, can you check, does that G, my G so constructed, oh, okay. What? Why is Jenny, just a second, I need to, she doesn't usually call me this early. Is everything okay?
Fine, I'm just asking when are you coming home?
Oh, I will call you back. Bye-bye. I'm still teaching. Okay, bye. All right, now I'm in trouble. I should just not have called back. That would have been smarter. Oh well. Just worried, like, has someone bit someone else and broke the skin? Has someone fallen and broken some limb? Like, what's the nature? I don't know. I think it's just she's curious. When I'm coming home, the answer is once I'm done teaching. All right, so I think G so constructed definitely will satisfy, F composed. I mean, we can try it out, right? If we look at, let's see here, F of what? F of X naught is equal to G of this, which is G of pi of X naught, which is G composed with pi of X naught for all X naught, right? Therefore, F is G composed with pi. Okay, good. Yay. All right. Okay. Moving along here. Why is it continuous, by the way? Why is G continuous? The previous theorem. Oh, because G composed with pi is F, which is continuous, therefore G is continuous by, as you just told me, Theorem 13.2. Woo! I'm glad you guys can remember something like 5 minutes after it's done, because I sure don't. Theorem 13.4. It's just sad. That's why you need students. Let's see here. Let X and Y be compact Hausdorff. Whoa. Whoa, whoa, whoa. X and Y compact Hausdorff. Both compact and Hausdorff. Compact Hausdorff. Compact Hausdorff spaces. All right. And F, a continuous function from X to Y. All right. Define equivalence relation in X by, well, this is the one we were just talking about. X naught is equivalent to X1 if and only if what? F of X naught equals to X1, F of X1, right? In other words, this is the fiber equivalence. Then, woo, X mod tilde is homeomorphic to Y. I think I missed a word here. What did I miss? Which word did I miss? Right. That is absolutely critical. Well, here I can write onto better. All right. So, how do we prove this? How do we prove this? Here we go. He says since the quotient space is the image of x under the continuous function pi, he says pi of x is equal to x tilde. All right, great. X mod tilde compact, right? Because this is compact and this is continuous, right? And what do we learn? The continuous image of a compact set is compact. And what else? He says let G be the continuous function from x mod tilde to y such that what? G composed with pi equals to f. Can we do that? Where is this G coming from? Theorem 13.3, right, says that there exists a G from the equivalence class, from the quotient set of x, right, with respect to the f fibers to y, such that G composed of pi is equal to f. And what does that tell us? Then G is what? G is continuous. And what else do we know? Is it injective? If we look at G of x naught is equal to, if G of x naught is equal to G of x1, right? If we set G of two different inputs equal, what does that say? Right, which means, so therefore G is 1 to 1. So let us count our chickens. We have G doing what? It is continuous, and it is doing what else? It is mapping into it's injective, right? It is onto by construction, right? Because, well, how do I know G is onto? Right, I mean, if G composed with F, if F is on, I mean, if F is onto, you know, here, if you don't believe me, you prove it, right? So let Y naught be in Y, then there exists X naught in X such that what? F of X naught equals to Y naught. Then G of what equals to Y naught? What I'm trying to say is injectivity and surjectivity of G are easy to prove. So I just, right, by construction. So G is continuous, it's 1 to 1, it's onto, and its image is where? Y. What is Y? Compact Hausdorff, right? And so what was our theorem? Theorem back in, it was a long time ago, but if we go back to theorem 6.7, which I will do,